Tonight, we're going to travel farther into the past than any human has ever gone. Not millions of years, not billions, but more than 13 billion years into a time before Earth existed, before the sun was born, and before our galaxy had fully taken shape. A time when the universe itself was still young. And somewhere within that ancient darkness, hidden among the first structures ever assembled by gravity, there was something waiting to be discovered. Tiny red lights, small enough to be overlooked, ancient enough to rewrite a chapter of cosmic history, and perhaps most strangely of all, one of them may have eventually become the black hole at the center of our own galaxy. But we'll come back to that later. Our story begins on a quiet patch of sky. If you step outside on a clear night and look upward, the sky appears crowded with stars. Yet almost everything you can see belongs to our own galaxy. The truly distant universe is hidden far beyond the reach of human eyes. To explore it, astronomers must do something remarkable. They point a telescope toward what appears to be nothing at all. No bright star, no visible galaxy, just darkness, and then they wait. For days, sometimes weeks, collecting every faint photon that arrives from the depths of space. This technique is called a deep field observation. Imagine holding a grain of sand at arm's length against the sky. The area hidden behind that tiny grain contains thousands of galaxies, each holding billions of stars. The universe is far more crowded than it appears. In 1995, the Hubble Space Telescope performed one of the most famous deep field observations in history. It revealed an astonishing truth. What looked empty was anything but empty. Galaxies filled the darkness. Every direction led to more galaxies, more stars, more history, more time. For decades, those images shaped humanity's understanding of the cosmos. Then a new telescope arrived, one that had been planned for more than 20 years. One designed to look farther than Hubble ever could, the James Webb Space Telescope. Unlike its predecessor, Webb was built to see a different kind of light that had traveled across almost the entire history of the universe. Light so ancient that by the time it reached us, it had been stretched into wavelengths invisible to human eyes. When Webb finally opened its golden mirrors and began observing the distant cosmos, astronomers expected new discoveries. They expected clearer images, older galaxies, perhaps a few surprises. What they did not expect was to find hundreds of strange red objects scattered through nearly every field image. Tiny red lights, sometimes appearing behind galaxies, sometimes between them, sometimes in places where nothing unusual should have existed at all. At first glance, they seemed unremarkable. Just small points of light, easy to ignore. But the more astronomers looked, the stranger they became. The objects appeared extraordinarily distant. Their light had been traveling toward Earth for more than 13 billion years. That meant Webb was not seeing them as they are today. It was seeing them as they were when the universe was still in its infancy. And yet these tiny objects seemed far too bright, far too compact, far too mature. It was as though someone had opened a history book to the earliest pages and discovered fully grown cities, standing where only villages should have existed. Something didn't fit. Over the months that followed, astronomers found more of them, then more, then hundreds more. Every new observation seemed to reveal additional red dots hiding in the background. The growing collection received a simple nickname, Little Red Dots, not because scientists understood them, but because nobody knew what else to call them. And that was where the mystery truly began. Because astronomy is often a science of patience, most discoveries arrive gradually. A clue here, a measurement there. Years of observation slowly assembling a larger picture. The little red dots refused to cooperate. Every answer seemed to create a new question. Why were they so bright? Why were they so small? Why did they appear almost exclusively during the universe's first billion years? And perhaps, most importantly, what exactly were we looking at? For nearly 4 years, nobody could say for certain. The dots remained silent. No clear explanation emerged. Some theories appeared promising before collapsing under closer inspection. Others solved one problem only to create 3 more. Meanwhile, the ancient red lights continued to stare back from the edge of time. Patient, unchanging, waiting. Tonight we're going to follow the trail they left behind. We'll travel into a universe that no longer exists. A universe younger, denser, and stranger than the one we know today. And before we can understand what these mysterious red dots might be, we first need to understand why previous generations of telescopes never saw them at all. Because the truth is that these objects were never hiding. They had been shining across the cosmos for billions of years. Humanity simply wasn't looking with the right eyes. If the little red dots had been shining for more than 13 billion years, why did nobody notice them sooner? After all, humanity has been studying the sky for centuries. We've built larger telescopes, more powerful telescopes. Telescopes capable of seeing galaxies billions of light years away. Surely someone should have found these strange objects long before James Webb arrived. The answer begins with a simple misunderstanding about light. When most of us think about light, we think about what our eyes can see. The colors of a sunset, the blue of the daytime sky, the pale glow of the moon. But visible light is only a tiny fraction of what actually exists. Imagine sitting beside a vast ocean. Now imagine that everything your eyes can detect occupies only a single drop of water from that entire sea. That is roughly how much of the universe's light is visible to us. Beyond that narrow window lies an enormous hidden world. Radio waves, microwaves, infrared light, ultraviolet light, X-rays, gamma rays. Different forms of the same phenomenon, different ways the universe communicates. Human eyes evolved to see only a small slice of that spectrum because it was useful for survival on Earth. The universe, however, is under no obligation to make itself convenient for us. And sometimes its most important secrets are hidden in places we cannot naturally see. For decades, the Hubble Space Telescope was humanity's greatest eye on the cosmos. Launched in 1990, Hubble transformed astronomy. It showed us galaxies colliding, nebulae giving birth to stars, black holes lurking in distant galaxies. It revealed a universe more beautiful and more complex than anyone had imagined. Entire generations of astronomers built their understanding of the cosmos using Hubble's observations. The telescope became so successful that people often assumed it could see everything worth seeing. But Hubble had limits. Every instrument does. Its greatest strength was visible light. The same basic kind of light your eyes are seeing right now. And that limitation would eventually become important. Because the universe itself has a habit of changing light during long journeys. To understand how, imagine drawing a wave in the sand. A smooth repeating pattern. Now grab both ends and slowly pull them apart. The wave stretches. The peaks move farther away from one another. The pattern becomes longer. Something similar happens to light. But instead of being stretched by hands, it is stretched by the expansion of space itself. This idea can feel strange at first. Most people imagine the universe expanding like an explosion, objects flying outward into empty space. But that isn't quite right. Space itself is expanding. The distances between galaxies are growing larger over time. The fabric of the universe is slowly stretching. And when light travels through that stretching fabric for billions of years, it stretches too. Its wavelength becomes longer. Its color shifts. Astronomers call this process redshift. The longer the journey, the greater the shift. A little stretching moves light slightly toward red. A great deal of stretching pushes it beyond red entirely, into infrared, into a realm invisible to human vision. This matters because the little red dots are unimaginably distant. The light we receive from them began its journey when the universe was still young. For more than 13 billion years, that light crossed expanding space. Every year adding a tiny amount of stretching, every billion years adding more, until eventually the original light no longer looked anything like it once did. What may have begun as visible light arrived at Earth as infrared. And infrared happened to be the one thing Hubble struggled to see. The dots weren't hidden because they were faint. They weren't hidden because they were rare. They were hidden because their ancient light had changed during its journey. Hubble was looking directly through them without realizing they were there. Imagine listening for birdsong while wearing headphones that only allow you to hear deep bass notes. The birds may be singing all around you. The sound may be loud. The information may be present. but your equipment simply isn't designed to detect it. That was Hubble's situation. The little red dots had been whispering across the cosmos for billions of years. Humanity just wasn't listening on the right frequency. James Webb was. From the very beginning, Webb was designed for a different mission. Its enormous golden mirrors weren't chosen for appearance. Gold happens to reflect infrared light exceptionally well. Its instruments were engineered specifically to detect the stretched light of the ancient universe. Even its operating temperature became part of the design. Infrared light is closely related to heat. Anything warm emits it, including telescopes, including electronics, including humans. If Webb became too warm, it would effectively blind itself. The faint signals from the distant universe would be lost beneath its own heat. To prevent that, engineers built a giant sunshield roughly the size of a tennis court. 5 delicate layers protecting the telescope from sunlight, allowing it to cool to temperatures colder than almost anywhere naturally found in the solar system. Only then could it detect the faint infrared whispers arriving from the dawn of cosmic history. It took decades of planning, years of construction, and one of the most complicated deployments ever attempted in space. But when Webb finally opened its mirrors and looked into the darkness, something remarkable happened. The universe immediately appeared larger, older, stranger. Galaxies emerged where none had been seen before. Structures appeared farther away than expected, and almost everywhere Webb looked, there were tiny red lights, hundreds of them, scattered across the background like forgotten embers from the earliest age of creation. The discovery carried an uncomfortable implication. Everything astronomers thought they knew about the universe's first billion years had been based on incomplete information. Not wrong, but incomplete. It was as if historians had spent decades studying an ancient civilization, only to discover an entire missing continent. The little red dots weren't a rare curiosity. They seemed to be everywhere, part of the ordinary landscape of the young universe. And that raised an even more intriguing question. If these objects were so common, what exactly was the early universe really like? Because the picture astronomers had been imagining for decades suddenly seemed far less certain. To answer that question, we need to travel even farther back to a time before galaxies like the Milky Way existed. Back to a universe less than 1 billion years old, a universe still learning how to build its very first structures. To understand why the little red dots seemed so unusual, we first need to leave behind everything familiar. The Earth, the Sun, the Milky Way, even the night sky itself. Because none of those things existed yet. Tonight, we're traveling to a universe less than 1 billion years old. A universe so young that, compared to its current age of nearly 14 billion years, it was still in its cosmic childhood. If the entire history of the universe were compressed into a single 80-year human lifetime, this period would occur before its 6th birthday. And yet somehow, this was the era where the little red dots appeared. To appreciate why that surprised astronomers, imagine arriving in a city and discovering skyscrapers before roads had been built, libraries before language existed, cathedrals before villages. Something would feel out of sequence. Something would seem to have arrived too early. That is exactly the feeling many researchers experienced when they began studying these mysterious objects. But before we get there, let's spend a moment in the universe they inhabited, because it was a place unlike anything we know today. After the Big Bang, the universe was hot beyond imagination. Not merely hot in the way stars are hot, not even hot in the way the center of stars are hot. It was so energetic that matter itself could barely exist. Particles appeared and disappeared constantly. The cosmos resembled a storm of pure energy. Then it began to expand, and as it expanded, it cooled. Slowly the chaos settled. The first atomic nuclei formed. Then, hundreds of thousands of years later, the first complete atoms appeared. Mostly hydrogen, mostly helium, the 2 simplest elements in nature. At that moment, the universe became transparent. Light was finally free to travel. Some of that ancient light is still crossing space today. We detect it as the cosmic microwave background. A faint glow surrounding us from every direction. A relic from an era so ancient, it feels almost unreachable. Yet compared to the little red dots, that was only the beginning of the story. For millions of years afterward, the universe entered a period sometimes called the Cosmic Dark Ages. It is one of the most poetic names in astronomy, not because anything sinister was happening, but because there were no stars, no galaxies, no planets, no visible light sources at all. Imagine drifting through an endless ocean of darkness, hydrogen stretching across unimaginable distances, no sunrise, no sunset, no constellations, no Milky Way arching across the heavens, only darkness and possibility. Gravity was quietly at work during this time, invisible and patient. Tiny differences in density left behind by the Big Bang slowly grew larger. Regions containing slightly more matter began pulling in even more matter. Clouds became denser. Filaments formed. Structures slowly emerged from what once seemed uniform. The universe was beginning to organize itself, very gradually, very carefully, like frost forming on a window or roots spreading through soil, and eventually the first stars ignited. No human has ever seen one, not directly. They existed too long ago. But astronomers believe these first stars were unlike the stars we know today. Many were enormous, hundreds of times more massive than our sun. They burned bright, burned fast, and lived brief lives. The universe's first generation of giants. For the first time, darkness began giving way to light. Across the young cosmos, isolated islands of starlight flickered into existence. Then more appeared, and more. Small structures began gathering around them. Primitive galaxies were born. Nothing like the majestic spirals we see today, nothing like the Milky Way. These early galaxies were smaller, messier, less organized. The universe was still learning, still experimenting, still assembling itself from simple ingredients. And according to the traditional picture of cosmic evolution, this process should have taken time. A great deal of time. Galaxies were expected to grow slowly. Stars would form, die, create heavier elements, build increasingly complex structures. One generation after another, like a forest, slowly expanding across a landscape, order emerging gradually from simplicity. For many years, this story seemed to fit the evidence remarkably well. Computer simulations reproduced it. Observations supported it. The timeline appeared sensible. Then James Webb arrived, and suddenly the earliest universe didn't look quite so simple anymore. The little red dots weren't the only surprise Webb discovered. The telescope also found galaxies that appeared larger than expected, brighter than expected, more mature than expected. Again and again, astronomers encountered structures that seemed slightly ahead of schedule, as though the young universe had developed faster than anyone anticipated. The little red dots became the most extreme example, because they appeared during a period when the universe should still have been relatively primitive. Yet these objects seemed compact, powerful, energetic, almost fully developed. The contrast was difficult to ignore. Imagine walking into a kindergarten classroom and finding a university professor sitting among the children. That is roughly how these objects appeared within the timeline of cosmic history. They simply looked too advanced for their age, and age was becoming the key issue. Because when astronomers measured the distances involved, they realized these dots weren't appearing 2 billion years after the Big Bang, or 3 billion years after. Many existed within the universe's first billion years, some even earlier. That meant whatever process created them had happened extraordinarily quickly, much faster than conventional expectations suggested. The discovery forced researchers to reconsider an uncomfortable possibility. Maybe the young universe wasn't as quiet as they had imagined. Maybe it wasn't slowly assembling itself piece by piece. Maybe, beneath the darkness of the cosmic dawn, something far more dramatic was happening. Perhaps giant structures were forming rapidly. Perhaps black holes were growing at astonishing rates. Perhaps entire chapters of cosmic history were missing from our models. Nobody knew yet, but the questions were becoming impossible to ignore. And there was another problem, a much bigger one. The more astronomers studied the little red dots, the brighter they appeared. Far brighter. Bright enough that simple explanations began falling apart. Because if the measurements were correct, these tiny objects were producing extraordinary amounts of energy. and the numbers were becoming increasingly difficult to explain. In the next chapter, we'll discover why the brightness of the little red dots became one of the greatest puzzles in modern astronomy. Because what seemed at first like a collection of faint red specks was beginning to look like something much more powerful, something that should not have been possible in the universe's first billion years. At first, the little red dots seemed mysterious, simply because they were there. But as astronomers gathered more data, a deeper problem emerged. The dots weren't merely ancient, they weren't merely distant, they appeared to be extraordinarily bright. And brightness in astronomy is often where the real story begins, because light is not free. Every photon carries energy, every glow has a source. And the brighter an object becomes, the more difficult it becomes to explain where that energy is coming from. The little red dots were about to become a lesson in just how extreme the early universe could be. Imagine standing alone in a dark valley at night. Far away on the horizon, you notice a single light. At first it seems insignificant, a distant glow against the darkness. But as you measure it more carefully, you realize something strange. The light isn't coming from a campfire, or a house, or even an entire city. It's coming from something vastly more powerful. Something producing enough energy to illuminate an entire continent. That was the feeling astronomers experienced when they began calculating the true brightness of the little red dots. The numbers seemed almost unreasonable. Some of these objects appeared capable of producing as much light as hundreds of billions of suns. Pause for a moment and consider that scale. Our sun is not a small object. Every second, it releases more energy than human civilization could use in hundreds of thousands of years. It powers Earth's climate, drives our weather, supports nearly all life on our planet. And yet, compared to the brightest little red dots, a single sun contributes almost nothing. The most luminous examples seemed capable of rivaling the total light output of entire galaxies. Not star clusters, not nebulae, entire galaxies. And somehow, they were doing it from regions that appeared astonishingly compact. That combination immediately raised alarms. Because brightness alone isn't unusual in astronomy. The universe contains many bright things. Large galaxies are bright. Quasars are bright. Massive clusters of stars are bright. But those objects are also large, very large, spread across enormous distances. The little red dots appeared different. They seemed to be concentrating enormous amounts of energy into remarkably small volumes of space. And that changes everything. Imagine compressing an entire city's worth of lights into a single apartment building. Then imagine compressing that apartment building into a single room. The smaller the space becomes, the harder it is to explain how all that energy can be produced and sustained. This is exactly the problem astronomers faced. The brightness suggested something enormous. The size suggested something tiny. The two measurements seemed to contradict each other. At first, researchers explored the simplest explanation. Perhaps the dots were dense collections of stars. After all, the early universe was rich with young stars. Young stars burn hotter than older stars, brighter than older stars. Maybe these objects were simply regions where vast numbers of stars had formed unusually close together. It sounded reasonable. For a while, it was one of the leading ideas. But then the calculations began, and the calculations were not kind. To produce the observed brightness, some of these objects would require staggering numbers of stars packed into incredibly small spaces. Not millions, not tens of millions, but billions upon billions of stars, all crowded together. The density required became increasingly absurd. Stars are massive objects. Each one possesses gravity. Place enough stars close together and they begin interacting violently. Orbits destabilize. Collisions occur. Entire systems become chaotic. Eventually, the structure tears itself apart. Theoretical models showed that clusters dense enough to explain the little red dots shouldn't remain stable for very long. Certainly not long enough to account for what Webb was observing. It was as if someone had proposed fitting an entire mountain range inside a small, suburban house. The idea sounded less convincing the more closely you examined it, and there was another clue. The light itself. Astronomers don't simply measure brightness, they study the character of light its fingerprints, its patterns, its hidden signatures. Every type of object leaves behind distinctive clues. Stars produce one kind of spectral signature, galaxies produce another, nebulae produce another. When researchers analyzed the light from the little red dots, they found something unexpected. The signatures didn't resemble ordinary stellar populations. The light seemed to be telling a different story. Something else was happening inside these objects, something more energetic, something more extreme. Gradually, the star cluster explanation began losing support, not because it was impossible, but because it failed to explain too many observations at once. The brightness, the compactness, the unusual spectra, the combination simply didn't fit. One by one, researchers began looking elsewhere, and that's when a darker possibility started gaining attention. Because there is one class of object in the universe capable of generating astonishing amounts of energy from surprisingly small regions of space, an object powered not by nuclear fusion, but by gravity itself, black holes. The phrase often brings to mind darkness, silence, absence. But active black holes are among the brightest things in existence. When gas falls toward a black hole, it doesn't disappear immediately. Instead, it spirals inward, faster and faster, hotter and hotter. The gas becomes compressed, heated and accelerated, until it shines with extraordinary intensity. In fact, matter falling into a black hole can convert energy more efficiently than the fusion reactions powering stars. A feeding black hole can outshine billions of suns. Suddenly, the impossible brightness of the little red dots seemed easier to understand. A black hole could explain the energy. A black hole could explain the compactness. A black hole could explain why these objects appeared so powerful despite their small size. For a brief moment, it seemed the mystery might be solved. But astronomy rarely makes things that easy. Because this new explanation immediately created another puzzle. Perhaps the biggest puzzle yet. If these objects really contained rapidly feeding black holes, they should have been screaming across the universe. Black holes like these don't stay quiet. They announce themselves. They produce X-rays, radio waves, ultraviolet radiation. They leave fingerprints everywhere. And yet, when astronomers searched for those signals, they found almost nothing. No cosmic shouting, no blazing X-ray beacons, no obvious evidence of feeding black holes. Only the same quiet red glow. The dots remained strangely silent. It was as if researchers had discovered the brightest lighthouse on Earth, and yet somehow couldn't find its beam. The contradiction became impossible to ignore. The brightness pointed toward black holes. The silence pointed away from them. Both observations appeared correct, and both couldn't be true at the same time. Unless something was hiding the source. Unless the universe had wrapped these objects inside a disguise so effective that it concealed some of the most energetic environments in the young cosmos. In the next chapter, we'll explore that possibility. Because the little red dots may not have been quiet at all. They may simply have been hidden behind one of the most remarkable veils the universe has ever created. If the little red dots truly contained rapidly growing black holes, they should have been among the easiest objects in the universe to identify. Not because black holes themselves emit light, they don't, but because the material falling toward them does. In fact, some of the brightest objects ever discovered owe their brilliance to black holes. This might sound strange at first. After all, black holes are famous for being dark. Their gravity is so strong that even light cannot escape once it crosses a certain boundary. Yet the region around a feeding black hole can become one of the most luminous places in existence. Imagine water swirling around the drain of a bathtub. Now replace that water with vast rivers of gas. Replace the bathtub with an object millions of times more massive than the sun. And replace minutes with millions of years. The gas doesn't fall straight inward. Instead, it spirals, faster and faster, tighter and tighter. As friction builds, temperatures climb. The material becomes so hot that it begins releasing enormous amounts of radiation. The result is an object called a quasar. For decades, quasars have been among the most powerful cosmic beacons known to science. Some outshine entire galaxies. Some can be detected from billions of light years away. Even when the black hole itself remains invisible, The surrounding activity announces its presence to the universe. And that's what made the little red dots so confusing. If black holes were responsible for their brightness, where was all the noise? Where were the X-rays? Where were the radio signals? Where were the unmistakable fingerprints astronomers had come to expect from actively feeding black holes? Again and again, researchers searched. Again and again, they came back empty-handed. The dots remained stubbornly quiet. Their energy output suggested something violent. Their appearance suggested something hidden. It was as though astronomers had discovered the glow of a giant furnace without finding any sign of the fire inside. For a while, this contradiction became one of the greatest obstacles to understanding the objects. Every explanation seemed incomplete. Every answer solved one problem while creating another. The brightness demanded an engine. The silence concealed it. And so attention began shifting toward a new possibility. Perhaps the black holes weren't absent. Perhaps they were buried. To understand this idea, imagine standing outside during a foggy night. Somewhere in the distance, a powerful lighthouse rotates across the coastline. Normally, its beam would be visible for miles. But tonight, the fog is extraordinarily thick. The light is still there. The lighthouse is still operating. The energy hasn't disappeared. Yet from where you stand, all you can see is a soft glow diffused through the mist. The source itself remains hidden. Something similar may have been happening around the little red dots. Surrounding each object could have been enormous clouds of gas. Not ordinary gas. Not the thin gas drifting between stars today, but dense, turbulent clouds heated by the extreme environment around a growing black hole. The radiation produced near the center would attempt to escape. X-rays, ultraviolet light, high-energy emissions. But before they could reach intergalactic space, they would collide with this surrounding material. Again and again, each collision stealing energy, each interaction transforming the radiation into something gentler, something softer, something redder. Instead of escaping as violent X-rays, much of the energy would emerge as infrared light, the very kind of light James Webb was built to detect. Suddenly, several mysteries began aligning. The brightness made sense. The compact size made sense, and perhaps most importantly, the silence made sense. The black holes had never been quiet. They had simply been wrapped inside a cocoon so dense that it transformed their most energetic emissions before they could travel freely into space. Nature had hidden some of the most powerful objects in the early universe behind an enormous veil, and for billions of years, that veil remained intact. There is something almost poetic about that idea. For most of cosmic history, humanity believed the universe revealed itself through light. If something shined brightly enough, eventually we would see it. The little red dots suggested a more complicated reality. Sometimes the universe doesn't hide things by making them faint. Sometimes it hides them by changing the way they appear. The monsters were never invisible. They simply wore disguises. And those disguises may have lasted for millions of years, perhaps tens of millions, long enough for the black holes inside to continue growing, long enough to become some of the largest objects in the young universe, long enough to challenge nearly every expectation astronomers had about how quickly black holes could form. Because even if the cocoon theory was correct, another problem remained. A very large problem. The black holes still appeared too massive, too mature, too old for their age. Growing a black hole is not easy, at least not according to the traditional picture. Most black holes begin their lives after the death of massive stars. A star lives, burns through its fuel, eventually collapses, and leaves behind a black hole. From there, growth becomes a slow process. Gas falls inward, matter accumulates, occasional mergers add mass. Over billions of years, a small black hole can become a very large one. That timeline works well in the modern universe. The difficulty is that the little red dots existed near the beginning of cosmic history. There simply wasn't much time available. Imagine planting an acorn in the morning and returning that evening to find a towering forest. You would immediately suspect that something unusual had happened. The same logic applied here. The universe seemed too young for black holes of this scale. Yet the evidence kept pointing in that direction. Some researchers began wondering whether the first black holes formed differently from those we see today. Perhaps the early universe possessed shortcuts, pathways no longer available in the modern cosmos, mechanisms that allowed enormous black holes to appear far more rapidly than anyone had expected. If that were true, then the little red dots weren't merely strange objects. They were fossils, remnants from a version of the universe that no longer exists, a time when matter behaved differently, when cosmic conditions were unique, when nature experimented with possibilities that later disappeared forever. And if we wanted to understand how these hidden giants formed, we would need to travel even deeper into the universe's earliest chapter. Back toward the first stars, back toward the first clouds of primordial gas, back toward the moment when darkness first began giving way to light. The idea was elegant, perhaps even beautiful. The little red dots were not strange new objects at all. Perhaps they were simply young supermassive black holes hidden inside vast cocoons of gas. For many astronomers, this explanation solved several problems at once. But like so many discoveries in science, solving one mystery only revealed another. Because a cocoon is not a permanent structure, at least it shouldn't be. Imagine building a campfire beneath a blanket. At first, the blanket traps the heat, the warmth accumulates, the air beneath becomes hotter and hotter. Eventually, something has to give. The blanket burns, or tears, or is blown aside by the pressure building underneath. The same basic principle should apply around a feeding black hole. The more material falls inward, the more energy is released. The more energy is released, the greater the pressure pushing outward. Over time, that pressure should begin clearing away the surrounding gas. This process is known as feedback. And feedback is one of the most important ideas in modern astrophysics. It acts like a natural regulator. Without it, black holes might grow indefinitely, galaxies might evolve differently. Entire regions of the universe could look unrecognizable compared to what we see today. Normally, feedback works remarkably well. A growing black hole begins producing radiation. That radiation pushes on nearby gas. Some of the gas is driven away. The food supply shrinks, growth slows, balance is restored. Yet the little red dots appeared to be ignoring this rule. Their cocoons remained intact. Their black holes continued feeding, and somehow the surrounding gas managed to absorb extraordinary amounts of energy without being completely blown apart. It was as if the universe had discovered a way to silence one of its loudest engines. For a while, researchers weren't sure whether such a configuration could even exist. The environment around a feeding black hole is not gentle. It is one of the most violent places known. Temperatures rise to millions of degrees. Particles accelerate to incredible speeds. Radiation floods outward in every direction. Nothing about that environment seems compatible with stability. And yet the observations suggested stability was exactly what existed. The cocoons endured. The black holes continued growing. The disguise remained effective. To understand why, astronomers began looking more closely at the gas itself. Not just its presence, but its state, its structure, its behavior, and what they found was remarkable. The gas surrounding these objects wasn't ordinary gas. It had become ionized. This sounds technical, but the underlying idea is surprisingly simple. Every atom contains positively charged particles in its nucleus and negatively charged electrons orbiting around it. Under normal circumstances, these charges balance one another. The atom remains electrically neutral. But when enough energy is introduced, electrons can be stripped away. The atom becomes charged, the gas becomes ionized, and once that happens, its behavior changes dramatically. Ionized gas interacts with radiation in ways that ordinary gas cannot. It becomes extraordinarily effective at absorbing energetic light, X-rays, ultraviolet radiation, high-energy emissions. Instead of allowing these forms of radiation to escape freely, the cocoon captures them, transforms them, reprocesses them. The energy doesn't disappear. It simply changes form. Like sunlight passing through stained glass. The original light remains present, but what emerges looks very different from what entered. Inside the little red dots, the process was occurring on a cosmic scale. Violent radiation generated near the black hole struck the cocoon. The cocoon absorbed it. The energy heated the gas glowed, and much of the energy ultimately escaped as infrared light. The soft red glow James Webb could see so clearly. Suddenly, the disguise became easier to understand. The cocoon wasn't merely hiding the black hole. It was transforming the black hole's voice, converting a scream into a whisper, a blaze into an ember, and for millions of years, that transformation may have remained astonishingly effective. But even the strongest disguise cannot last forever, because while the cocoon was absorbing energy, the black hole at its center continued feeding, continued growing, continued changing its environment. Little by little, the balance shifted. The gas closest to the black hole was consumed. Regions became thinner. Turbulence created weak spots. Density varied from place to place. What had once been a nearly complete shell slowly became imperfect. Tiny cracks began appearing. At first, those cracks were insignificant. A small opening here, a thin region there. But in cosmic systems, small changes often lead to larger ones. Once a gap forms, radiation escapes more easily. That escaping radiation weakens nearby material, which creates larger gaps, which allows even more radiation to escape. A chain reaction begins. The cocoon starts losing its grip. Imagine an old dam holding back an enormous reservoir. For years, perhaps centuries, the structure remains intact. Then one day, a small fracture appears. Water begins leaking through. The crack widens. Pressure increases. And eventually, the dam can no longer contain what lies behind it. Astronomers suspected something similar might happen around the little red dots. The cocoon wasn't a permanent prison. It was a temporary phase, a stage in the life of a growing black hole. And if that idea was correct, there should be evidence. Somewhere among the thousands of dots, somewhere in the vast archive of observations, there should be examples caught in the act of transition. Objects no longer completely hidden, but not yet fully revealed. Objects standing between two identities. Neither silent cocoon nor blazing quasar, something in between. For years, researchers searched for exactly that. And eventually, one of the ancient red dots appeared to provide the clue they had been waiting for. A faint signal, barely detectable, easy to miss, yet potentially one of the most important observations ever made about the early universe. Because after billions of years of silence, one of the little red dots finally seemed to whisper back. For nearly 4 years, the little red dots remained frustratingly quiet. Astronomers had measurements, theories, computer models, spectral data, and growing confidence that hidden black holes were involved. But confidence is not proof. Science moves forward most carefully when extraordinary claims are involved. And claiming that the early universe was filled with rapidly growing black holes was certainly extraordinary. Researchers needed something more direct, something that could slip through the cocoon, something capable of revealing what was happening inside. That something was X-rays. Unlike visible light or infrared radiation, X-rays are produced in some of the most extreme environments in the cosmos. They emerge from exploding stars, neutron stars, and perhaps most importantly, from matter spiraling into black holes. For decades, X-rays had served as one of astronomy's most reliable indicators of active black holes. Find strong X-ray emissions, and chances are something extraordinary is happening nearby. The problem was that the little red dots didn't appear to produce any, at least not enough to detect. Again and again, observatories searched. Again and again, the results came back empty. The cocoons seemed almost perfect. If black holes were hiding inside, they were hiding exceptionally well. But perfection is rare in nature. Even mountains erode. Even stars eventually exhaust their fuel. And perhaps even the thick cocoons surrounding the little red dots could not remain, completely sealed forever. As observations accumulated, researchers began wondering whether some of the dots might represent different stages of the same story. Perhaps the youngest objects remained entirely hidden. Perhaps older ones had begun to emerge. Perhaps somewhere among the thousands of known dots there existed examples caught in the middle of the transformation. Not fully concealed, not fully exposed. A brief transitional phase, a moment when the disguise was starting to fail. If such objects existed, Astronomers expected them to be rare. The timing would be difficult. The transition itself might last only a fraction of the object's lifetime. Finding one would be like photographing a butterfly while it was still emerging from its chrysalis. Possible, but unlikely. Then, eventually, a breakthrough arrived. Researchers combined observations from James Webb with data collected by another remarkable instrument, the Chandra X-ray Observatory. Unlike Webb, which specializes in infrared light, Chandra is designed specifically to study the high-energy universe. It searches for X-rays, for signs of violent cosmic events, for clues hidden within the universe's most energetic environments. Together, the two telescopes provided something neither could achieve alone: a more complete picture. Two different windows looking into the same ancient past, and within that shared view, astronomers found something unexpected. One particular little red dot appeared to be emitting a faint X-ray signal, not a strong signal, not the overwhelming beacon expected from a fully exposed quasar, but enough to stand out, enough to attract attention, enough to suggest that something inside the cocoon was finally becoming visible. The discovery may sound modest, a faint signal from a single distant object, but its implications were enormous, because until that moment, the buried black hole model had remained largely indirect. It explained the observations, it fit the evidence, but direct confirmation remained elusive. Now, for the first time, astronomers had something more tangible. A glimpse through the cracks. Imagine standing outside a sealed building at night. For years, you have suspected powerful machinery is operating inside. You hear faint vibrations. You notice heat escaping through the walls. You see occasional flickers beneath the doors. Everything suggests activity, but you still cannot see the machines themselves. Then one day a small window opens, only slightly, only briefly. Yet through that opening, you catch a glimpse of what lies within. The machinery was there all along. The little red dot seemed to offer exactly that kind of moment. The cocoon had not vanished completely. The X-rays remained weak. The object was still heavily obscured. But it appeared that small gaps had formed in the surrounding gas. Tiny openings through which high-energy radiation could finally escape. The black hole wasn't fully revealed, but it was no longer perfectly hidden. And suddenly a larger story began taking shape. Perhaps the little red dots weren't a separate category of object at all. Perhaps they were simply an early phase in the life of something astronomers already knew well. A young phase, a hidden phase, a childhood stage. The beginning of a journey that would eventually lead to quasars, and perhaps, much later, to the quiet supermassive black holes we see today at the centers of galaxies. The idea was surprisingly elegant. First, a black hole forms within a dense environment rich in gas. The surrounding cocoon entraps much of its radiation. The object appears as a little red dot, bright, compact, mysterious. Over time, the black hole continues feeding. The cocoon becomes thinner. Radiation begins leaking outward. The object enters a transitional stage, a stage similar to the one Chandra may have detected. Eventually, enough material is cleared away. The cocoon breaks apart. The hidden giant emerges. The object becomes a visible quasar, brilliant, powerful, impossible to ignore. Millions or billions of years later, as the available fuel supply diminishes, the black hole settles into a quieter existence, still massive, still present, but no longer blazing across the cosmos. If this sequence is correct, then the little red dots are not merely mysterious relics from the early universe. They are snapshots of growth, snapshots of transformation, photographs taken during one of the most important stages in the life of a supermassive black hole. And perhaps even more remarkably, they may represent a stage that every giant black hole once experienced, including those at the centers of galaxies we know today, including the one at the center of the Milky Way. Suddenly, the little red dots felt less like distant curiosities and more like ancient ancestors, tiny red lights scattered across the early universe, each one potentially marking the birthplace of a future cosmic giant. But this realization raised another question, perhaps the most important question yet. If these objects really were young, supermassive black holes, how had they become so massive so quickly? Because even with a cocoon hiding their radiation, even with abundant supplies of gas, the timeline still seemed impossibly short. The universe was less than 1 billion years old. And yet these objects already appeared enormous. Somehow, nature had found a way to build giants almost immediately after the first stars appeared. And understanding how that happened would take us even closer to the beginning itself. To understand how these hidden giants appeared so early, we need to leave behind the modern universe once again. Because the universe that produced the little red dots was operating under conditions that no longer exist today. The galaxies around us now are old, mature, well-organized. Stars are spread across enormous structures that have spent billions of years evolving. Matter is relatively dispersed. Space is vast, quiet, diluted. The early universe was different, very different. Everything was closer together, denser, more chaotic, more crowded. If you could somehow travel back 13 billion years and observe the young cosmos, you might barely recognize it. Galaxies were smaller. Distances between structures were shorter. Vast rivers of gas stretched across space. Gravity was pulling matter together at extraordinary rates. The universe was still assembling itself, still building the foundations that would eventually become everything we see today. And in that environment, black holes may have had access to something modern black holes rarely enjoy: an almost unlimited supply of fuel. Imagine standing beside a small stream. No matter how efficiently you collect water, the amount available remains limited. Now imagine standing in the middle of a flood. Water rushes toward you from every direction. The problem is no longer finding a supply. The problem is keeping up with it. Many astronomers believe the first giant black holes may have existed in something closer to the second scenario. The young universe contained enormous filaments of gas, vast cosmic rivers connecting one growing structure to another. These filaments stretched across millions of light years, and they carried extraordinary quantities of hydrogen and helium toward regions where gravity was strongest. The black holes forming within those regions may have found themselves sitting directly in the path of these rivers. Instead of feeding from a small local supply of gas, they may have been receiving fresh material continuously. Year after year, million year after million year, fed not by a pond, but by a network of cosmic highways. This idea helps explain one of the most puzzling aspects of the little red dots: their growth. Because according to traditional models, black holes shouldn't be able to gain mass indefinitely at whatever rate they choose. There is supposed to be a limit. As material falls inward, radiation pushes outward. The stronger the feeding becomes, the stronger the resistance becomes. Eventually, a balance is reached. Astronomers call this balance the Eddington limit. For decades, it has served as one of the fundamental guidelines governing black hole growth. In simple terms, it represents nature's speed limit, a point where growth becomes self-regulating. Feed too quickly, and the resulting radiation begins pushing material away. Slowly applying the brakes, but the little red dots seemed unwilling to obey that expectation, or at least not completely. Their estimated masses suggested they had grown much faster than standard timelines allowed, which forced researchers to consider an intriguing possibility. Perhaps the Eddington limit behaves differently under the extreme conditions of the early universe. Imagine trying to stop a river with a fan. The fan may generate wind, the wind may push against the water, but if the river becomes powerful enough, the resistance barely matters. Some theoretical models suggest the earliest black holes may have experienced periods of what astronomers call super-Eddington accretion, a complicated phrase describing something surprisingly straightforward: growth beyond the expected limit, growth occurring faster than traditional models predict. Not forever, not continuously, but perhaps long enough to make an enormous difference. A black hole that occasionally exceeds the normal growth rate gains a tremendous advantage. Each increase in mass strengthens its gravity. Stronger gravity attracts more material. More material enables more growth. A feedback loop develops. The giant becomes larger. The larger giant becomes larger still. What begins as a small head start eventually turns into a dramatic lead. And this may explain why the little red dots appear so mature despite their young age. But there is another possibility, one that many astronomers find even more fascinating, because perhaps these black holes didn't start small at all. For most of the modern universe, black holes begin with stars. A massive star lives, a massive star dies, a black hole remains. The process is familiar, predictable, repeated countless times across cosmic history. But what if the earliest universe occasionally skipped that step? What if some black holes were born large from the beginning? This idea is known as direct collapse, and it may represent one of the most important concepts in the entire story of the little red dots. Imagine a gigantic cloud of primordial gas, hundreds of thousands of times more massive than the Sun, perhaps even larger. Under ordinary circumstances, such a cloud fragments. Smaller regions collapse independently. Stars form. A galaxy gradually emerges, but under certain rare conditions, fragmentation may not occur. The cloud remains intact. Gravity continues pulling inward. The entire structure collapses as a single system. No star, no supernova, no intermediate step, just an enormous concentration of matter falling directly toward catastrophe. Eventually, gravity wins completely, and a massive black hole forms, not with the mass of a dying star, but with the mass of an entire cloud. A tremendous head start. Suddenly, the timeline becomes less impossible. A black hole beginning its life with hundreds of thousands of solar masses needs far less time to reach. Millions of solar masses. What once seemed absurd begins to look achievable. And remarkably, the conditions required for direct collapse may have existed only during the universe's earliest chapter. That possibility carries profound implications, because it suggests the little red dots are not merely ancient objects. They may be relics from a mode of cosmic creation that disappeared forever, a process nature once used freely, then abandoned. The modern universe no longer contains the same environment, the same densities, the same primordial conditions, the same vast reservoirs of untouched hydrogen and helium. Whatever factory produced the first giant black holes appears to have shut down billions of years ago. The little red dots may be among the last surviving clues that it ever existed. And perhaps the most remarkable part of all is that some physicists predicted something like this long before James Webb ever launched, years before the telescope unfolded its mirrors, years before the first red dots appeared in deep-field images. A handful of researchers had already imagined objects that sounded surprisingly similar, objects unlike ordinary stars, unlike ordinary black holes, something suspended between the two, a strange theoretical possibility that spent decades living mostly on paper, until the universe suddenly began offering evidence that it might be real. Long before James Webb revealed the little red dots, a few astrophysicists were already thinking about a strange possibility, not because they had observed it, not because they had evidence for it, but because mathematics suggested it might exist. The idea was unusual enough that many researchers treated it as an interesting curiosity rather than a serious prediction, a theoretical object living somewhere between a star and a black hole, something that should have appeared only during the universe's earliest era, an object sometimes called a quasi-star, or more poetically, a black hole star. At first glance, the phrase sounds contradictory. Stars and black holes seem like opposites. Stars shine, black holes consume. Stars produce light, black holes trap it. Yet, under the extraordinary conditions of the young universe, nature may have briefly blurred the distinction. Imagine an enormous cloud of primordial hydrogen and helium collapsing under its own gravity. Not thousands of solar masses, not tens of thousands, but perhaps hundreds of thousands, perhaps more. The cloud continues shrinking, growing hotter, growing denser. Gravity strengthens with every passing moment. In a normal scenario, stars would begin forming throughout the cloud. The structure would fragment into smaller pieces. A cluster of stars would emerge. But suppose fragmentation never happens. Suppose the entire cloud remains intact. Gravity continues tightening its grip. The center becomes denser and denser until eventually a black hole forms directly within the heart of the cloud. Now something remarkable occurs. The collapse doesn't stop. The surrounding gas remains in place. The black hole begins feeding, growing, consuming material from the inside. Meanwhile, the energy released by that feeding process pushes outward against the rest of the cloud. A strange balance develops. Gravity pulls inward, radiation pushes outward, the black hole grows, the cloud survives. From a distance, the entire structure might resemble an enormous star. Bright, massive, glowing, yet hidden inside would be something completely different. A growing black hole, a monster disguised as a star. For years, this idea remained largely theoretical. There was no way to test it. No telescope powerful enough to examine the earliest stages of cosmic history in sufficient detail. The concept remained parked in academic papers. Interesting, exotic, largely unverified. Then James Webb began sending data home, and suddenly some of the little red dots started looking surprisingly familiar. Not identical, not perfect matches, but familiar enough to make researchers pay attention. Many of the characteristics lined up: extreme brightness, compact size, heavy obscuration, rapid growth, a dense surrounding envelope capable of trapping radiation. The similarities were difficult to ignore. This doesn't mean the little red dots are definitely quasi-stars. The majority of astronomers still favor the simpler explanation: rapidly growing black holes hidden inside dense cocoons of gas. That model explains much of the available evidence remarkably well. But science rarely rewards certainty too early. Some of the most extreme little red dots continue resisting simple explanations. And for those objects, the quasi-star idea remains surprisingly difficult to dismiss. Perhaps some of the dots belong to one category. Perhaps others belong to another. Nature is under no obligation to make every object fit neatly into a single box. The universe often prefers complexity, especially in its earliest chapters, and that may be exactly what we're seeing. Not one mystery, but several overlapping mysteries sharing similar appearances. The deeper researchers look, the more diverse the population appears to become. Some objects may be hidden black holes, others may represent transitional stages, others may preserve evidence of formation mechanisms that no longer exist anywhere in the modern cosmos, and all of them point toward the same conclusion. The early universe was far stranger than astronomers once imagined. For decades, many textbooks presented a relatively straightforward story. Stars formed first. Black holes formed later. Small structures gradually became larger structures. Everything unfolded in a slow and orderly progression. The little red dots suggest reality may have been considerably messier and considerably faster, because regardless of whether they are buried black holes, quasi-stars, or some combination of both, one fact remains difficult to escape. The earliest universe was building enormous objects with extraordinary efficiency. Almost immediately after the first stars appeared, something accelerated the process. Something allowed giant black holes to emerge astonishingly quickly, and that realization has consequences far beyond the little red dots themselves. Because every large galaxy in the modern universe contains a supermassive black hole, including our own. At the center of the Milky Way sits Sagittarius A, a gravitational giant containing roughly 4 million times the mass of our Sun. It rests about 26,000 light-years from Earth, quiet by modern standards, mostly dormant, occasionally feeding on small amounts of gas drifting too close. Yet despite its calm appearance today, Sagittarius A has not always existed in this form. Like every object in the universe, it had a beginning, and for a long time, astronomers assumed they understood that beginning. A small black hole forms. It grows gradually. Mergers add mass. Billions of years pass. Eventually, a supermassive black hole emerges. Simple, reasonable, comfortable. The little red dots have complicated that story. Because if direct collapse occurred, if giant black hole seeds formed almost immediately, if buried growth phases were common throughout the early universe, then Sagittarius A may have started life very differently than we once imagined. Picture the universe 13 billion years ago. No Earth, no Sun, no Milky Way spiral arms stretching across the darkness. Only growing clouds of primordial gas, emerging galaxies, and scattered among them, countless tiny red lights. Somewhere within that population One of those lights may have occupied the region that would eventually become our galaxy. A hidden giant feeding within its cocoon, invisible light, quiet to outside observers, growing, waiting, becoming. Over billions of years, stars gathered around it. Galactic structures formed, mergers reshaped its environment, the cocoon disappeared, the black hole evolved, and eventually the Milky Way emerged around it. If that picture is correct, then the little red dots are not merely distant curiosities. They are glimpses of ancestry, snapshots from the childhood of objects that still exist today, including one that quietly anchors our entire galaxy. There is something deeply humbling about that possibility. Every night, the stars of the Milky Way arc overhead. Invisible beyond them, at the galaxy's center rests Sagittarius A, a black hole so ancient that its origins may reach back to an era before our galaxy existed, before our sun existed, before planets existed, and perhaps long before any observer existed to witness its birth. The little red dots may be showing us those forgotten beginnings, not as they are now, but as they once were, young, hidden, still becoming what they would eventually become. And yet, even if this story is correct, another mystery remains, perhaps the biggest one of all, because the little red dots are not rare, they are everywhere, and that raises an uncomfortable question. If the early universe was producing giant black holes on such an enormous scale, what does that say about our entire understanding of how the universe grew up? One of the most surprising aspects of the little red dots is not what they are. It's how many of them exist. If astronomers had discovered a single object like this, the explanation might have been simple. Rare things happen in the universe. Unusual events occur. Sometimes nature produces exceptions. But the little red dots are not isolated anomalies. They appear again and again, in image after image, field after field. Wherever James Webb peers deeply enough into the ancient universe, more of them seem to emerge from the darkness. That changes the nature of the mystery entirely. A single strange object raises questions. Thousands of strange objects raise concerns, because when something appears repeatedly across the cosmos, it is usually revealing a fundamental truth about how nature operates. The little red dots are not rare accidents. They appear to be part of the architecture of the young universe itself. And that realization has forced astronomers to re-examine assumptions that seemed secure only a few years ago. For decades, the standard picture of cosmic evolution appeared straightforward. Small structures formed first. Larger structures appeared later. Galaxies slowly assembled themselves through mergers and gradual growth. Black holes evolved alongside them. Everything happened according to a timeline that seemed logical and predictable. The model worked remarkably well. In fact, it still works remarkably well for much of cosmic history. The difficulty appears when we travel back toward the beginning, because the earliest universe keeps refusing to behave exactly as expected. The little red dots are only one example. James Webb has also revealed surprisingly mature galaxies appearing earlier than anticipated. Galaxies that seem too massive, too organized, too evolved. Structures that appear to have developed ahead of schedule. The further astronomers look into the first billion years, the more often they encounter objects that seem slightly older than they should be. Not impossibly old, not necessarily requiring entirely new physics, but old enough to create tension, old enough to suggest that some important piece of the story may be missing. Imagine trying to understand the history of a civilization by studying a collection of photographs. The earliest images should show simple villages, primitive roads, small communities. Instead, the photographs reveal sprawling cities appearing almost immediately. The cities clearly exist. The evidence is undeniable. The challenge becomes explaining how they emerged so quickly. That is the situation astronomers increasingly find themselves facing. The universe appears to have been astonishingly productive during its first billion years. Stars formed, galaxies formed, black holes formed, and many of them seem to have grown with remarkable speed, perhaps faster than anyone anticipated. This does not mean current cosmology is wrong. That point is important. Scientific models rarely collapse overnight. Reality is usually more subtle. Most often, Observations reveal areas where existing theories need refinement rather than replacement. The foundations remain intact, the details evolve, and that may be exactly what is happening here. The little red dots are not destroying our understanding of the universe. They are expanding it, showing us regions of cosmic history that previous telescopes simply could not access. For most of human history, the first billion years of the universe were largely hidden. We could infer, estimate, simulate, but direct observations remained limited. James Webb changed that. For the first time, astronomers gained the ability to study this period in extraordinary detail. And whenever humanity gains access to a new frontier, surprises tend to follow. Galileo pointed a telescope at Jupiter and found moons. Hubble revealed galaxies beyond the Milky Way. Now Webb is revealing a universe crowded with objects nobody expected to find in such abundance. History suggests that this is exactly how science progresses. Not through certainty, but through discovery. Each answer opens new questions. Each observation reveals new layers of complexity. And nowhere is that more apparent than in the little red dots. Because even if we accept the buried black hole model, even if direct collapse explains their formation, even if cosmic filaments supplied the fuel they needed, important mysteries remain. Researchers still debate their exact masses, still debate their growth rates, still debate whether all of them belong to the same category of object. Some observations suggest multiple populations may be hiding beneath the same appearance. Some dots may be buried black holes. Others may represent transitional phases. Still others may belong to categories we have not fully recognized yet. The story remains unfinished, and that may be the most exciting part. The universe is not a completed book. It is a manuscript still being written. Every new observation adds another page. Every new telescope reveals another chapter. The little red dots remind us that some of the most important discoveries occur not when questions are answered, but when entirely new questions appear. For centuries, humanity assumed the early universe was relatively simple, dark, sparse, gradually assembling itself over immense stretches of time. Today, that picture looks far richer, far busier, far more dynamic. The first billion years may have been one of the most creative periods in cosmic history. A time when giant black holes emerged, when galaxies assembled themselves at extraordinary speed, when conditions existed that may never exist again. A universe experimenting with possibilities, testing pathways, building foundations, and perhaps leaving behind clues that still influence everything we see around us today. Because the stars above us, the galaxies surrounding us, even the black hole resting silently at the Milky Way's center, may all trace part of their history back to those ancient red lights. Tiny points of infrared glow hidden within the darkness of the cosmic dawn, invisible for billions of years, waiting patiently for a telescope capable of seeing them, waiting for a civilization capable of understanding what they were trying to tell us. And perhaps the strangest realization of all is this: the little red dots are not really showing us black holes, or galaxies, or even the early universe. Not directly. What they are truly revealing is a universe that no longer exists, a universe denser than today's, hotter than today's, more chaotic, more crowded, a universe operating under conditions that vanished billions of years ago. The objects survived, the light survived, but the environment that created them disappeared long ago. What James Webb is showing us is not merely distant space, it is a lost world. A chapter of cosmic history preserved only because light travels slowly. And because that ancient light is only arriving now, we have been given a rare opportunity to witness a time before the Milky Way was fully formed, before the Earth existed, before the sun had begun shining, a glimpse into an era that shaped everything that followed. And as we follow those ancient photons farther and farther back through time, we eventually reach a boundary, a place where every answer leads to an older question, a place where the story of the little red dots becomes inseparable from the story of the universe itself. There is another reason the little red dots have captured the imagination of astronomers around the world. It goes beyond black holes, beyond galaxies, beyond even the question of how the first giant structures formed. Because hidden within these ancient objects is a glimpse of something far rarer, a universe that no longer exists. Not a distant place, not a parallel universe, not another dimension, our universe, the same cosmos we inhabit today, but at a stage so early and so different that it might feel almost alien to us. Imagine standing beside an ancient river. The water flowing past you today is not the same water that flowed 1,000 years ago. The river survives. The landscape survives. But the world that once surrounded it has vanished. The forests are different. The animals are different. The climate is different. Time has transformed everything. The universe works much the same way. The cosmos we see today is not the cosmos that produced the little red dots. It is older, calmer, more settled. The great construction projects of cosmic history are largely complete. Galaxies have matured. Stars have lived and died through countless generations. Heavy elements have become common. Planets have formed. Life has emerged. Civilizations have appeared. But when the little red dots were shining, almost none of that existed. The universe was still discovering what it would become. Hydrogen and helium dominated nearly everything. The heavier elements that make up mountains, oceans, trees, and human beings were incredibly rare. There was no Earth, no moon, no solar system, not even the familiar spiral structure of the Milky Way. Many of the things we consider permanent features of reality simply hadn't formed yet, and because of that, nature had opportunities it no longer possesses today. The first billion years were a unique era, a brief chapter when the rules of cosmic evolution produced outcomes that may never happen again. This idea is easy to overlook. When we think about the universe, we often imagine its laws as eternal and unchanging, and in many ways they are. Gravity today behaves much as it did 13 billion years ago. Light still travels at the same speed. Atoms still obey the same fundamental principles. Yet the environment in which those laws operate changes dramatically over time. The same ingredients can produce very different results depending on the conditions. Consider snowflakes. The laws governing water molecules remain constant, but snowflakes only form within a narrow range of temperatures and pressures. Change the environment, and entirely different structures emerge. The early universe may have been operating within its own rare window of possibility. A period when immense clouds of primordial gas could collapse in ways no longer common. A period when giant black hole seeds could form unusually quickly. A period when dense cocoons could surround rapidly growing cosmic giants. A period capable of producing the little red dots, and then that window closed. As generations of stars lived and died, they enriched the universe with heavier elements. Those elements changed the behavior of gas clouds, changed the way stars formed, changed the way galaxies evolved. The universe slowly became more complex, more structured, more familiar. The conditions that once existed faded away, like morning fog disappearing beneath sunlight. This is one reason the little red dots feel so special. They may not simply be ancient objects. They may be survivors from an extinct era, the astrophysical equivalent of fossils. Not fossils preserved in stone, but fossils preserved in light, messages carried across billions of years. Evidence from a chapter of cosmic history that would otherwise be lost forever. And perhaps that is what makes astronomy so different from most sciences. Geologists can examine ancient rocks. Archaeologists can excavate ancient cities. Paleontologists can uncover ancient bones. But astronomers possess something even stranger, a machine for looking backward through time itself. Every time we observe a distant galaxy, we are seeing history. Not metaphorically, literally. The farther away an object is, the older the version of reality we observe. James Webb is not merely looking into deep space. It is looking into deep time. The little red dots are visible today only because their ancient light spent more than 13 billion years crossing the universe. Every photon arriving at Webb's mirrors began its journey before Earth existed, before oceans formed, before the first cell emerged on our planet, before anything alive had ever looked upward and wondered what lay beyond the stars. Those photons have been traveling ever since, crossing expanding space, passing galaxies, passing clusters of galaxies, passing entire civilizations. that rose and vanished before the light even reached our corner of the cosmos. And eventually, after a journey longer than human language can comfortably describe, they arrived. Not at random, but at a moment when a species capable of understanding them finally existed. There is something deeply moving about that thought. The universe spent billions of years sending a message, and only recently did anyone become capable of reading it. The message was not written in words, or numbers, or symbols. It was written in light, a faint red glow from a forgotten age. And hidden within that glow was a story. A story about giant black holes, about vanished environments, about a young universe growing faster and more creatively than anyone expected. A story that remained unread for nearly the entire history of the cosmos. Until now. Yet perhaps the most extraordinary part is that the story is still unfinished. Because every answer James Webb provides seems to reveal additional mysteries waiting beyond it. The little red dots have given us a glimpse of a lost universe, but they have also reminded us how much remains unknown, how many chapters are still missing, how many ancient secrets remain hidden in the darkness beyond our current reach. And as we prepare to leave the first billion years behind and return to the present, one final thought remains. The universe that created the little red dots may be gone forever, but its light is still arriving, even now, even tonight. Still crossing the darkness between galaxies, still carrying whispers from a world that disappeared billions of years ago. And now, as our journey through the first billion years of cosmic history begins to draw to a close, it's worth returning to where we started, not to the distant edge of the observable universe, not to a hidden black hole wrapped inside a cocoon of gas, not to the strange red lights discovered by James Webb, but to something much simpler. The night sky, a sky that countless generations have looked upon with wonder, a sky that appears calm, familiar, timeless. From the surface of Earth, the universe often feels permanent. The stars seem fixed in place, the constellations appear unchanged. The heavens above us feel steady and enduring. Yet everything we have explored tonight tells a different story. The universe is not still. It never has been. Every star overhead has a history. Every galaxy carries memories of older galaxies. Every black hole traces its origins to events that unfolded billions of years ago. The cosmos is a story in motion, and we happen to exist in the middle of it. Somewhere above us tonight, beyond the stars visible to human eyes, ancient photons are still traveling through the darkness. Some began their journey before the Milky Way fully existed. Some left their homes before our sun was born. Some departed long before Earth became a world capable of supporting life. For billions upon billions of years, they crossed an expanding universe, passing through regions of space no human will ever visit, passing galaxies that had not yet formed when their journey began, passing civilizations that would rise and vanish in less time than a single step of their cosmic voyage. And eventually, a tiny fraction of those photons reached us. Not because they were searching for us, not because the universe intended them to arrive, but simply because light travels onward, patiently, relentlessly, crossing unimaginable distances one moment at a time. There is something comforting about that. The universe often appears vast beyond comprehension. Its distances are enormous, its timescales dwarf human experience, its structures stretch across dimensions difficult for the mind to grasp. Yet despite that immensity, the light from the little red dots found its way here, into the mirrors of a telescope orbiting far from Earth, into the computers of scientists, into the story we've shared tonight. The gap between then and now suddenly feels a little smaller, a little more connected. The first billion years of cosmic history are no longer completely hidden. The darkness has become slightly less dark. And perhaps that is one of the most beautiful aspects of discovery. Not that it provides certainty, but that it allows us to see a little farther than before. The little red dots have not solved every mystery. Far from it. Questions remain. Debates continue. New observations will undoubtedly reshape parts of the story. That is the nature of science. Every answer becomes the beginning of another question. Every horizon reveals a more distant horizon waiting beyond it. Yet, even incomplete knowledge carries its own kind of wonder. Because what we've learned is extraordinary enough. The universe's earliest age was not empty. It was not simple. It was not quietly waiting for galaxies to emerge. It was alive with activity, filled with growth, filled with creation, filled with hidden giants wrapped in clouds of primordial gas, tiny red lights scattered throughout the darkness, each one carrying clues from a world that no longer exists. And perhaps somewhere among those ancient lights was an object destined to become something familiar, a future galactic core, a future supermassive black hole, perhaps even the ancestor of Sagittarius A itself, a silent giant waiting at the center of the Milky Way. If that possibility is true, then the story of our galaxy began far earlier than we once imagined, long before Earth, long before the Sun, long before there was anyone to witness it. The foundations were already being laid. The future was already taking shape, and hidden within the darkness of the cosmic dawn, the earliest chapters of our own story may have already been unfolding. Tonight, those chapters feel a little closer, not because we traveled across space, but because we traveled across time, back through billions of years of history, back beyond familiar stars, back beyond the birth of galaxies, back toward a universe still discovering what it would become. And perhaps that is the greatest gift James Webb has given us. Not merely new images, not merely new data, but perspective. A reminder that everything around us belongs to a story far larger than ourselves. The air we breathe, the atoms in our bodies, the planet beneath our feet, the galaxy surrounding us, all are connected to events that unfolded in a distant age beyond memory, an age whose light is only arriving now. So the next time you find yourself beneath a clear night sky, take a moment to look upward, beyond the familiar stars, beyond the faint band of the Milky Way, beyond everything visible to the naked eye. Somewhere out there, ancient photons continue their endless journey. Some left home before Earth existed. Some began traveling before the first oceans formed. Some have crossed nearly the entire observable universe to reach this moment. And even now, as the night grows quieter and the stars slowly drift overhead, those travelers continue onward, crossing the darkness, carrying their stories, linking the present to a forgotten past, a past filled with hidden giants, ancient red lights, and a universe still learning how to become the cosmos we know today. Thank you for joining me on this journey through the cosmic dawn, and wherever you are beneath the night sky. I hope you have a peaceful evening. Good night.